Hello, chemistry students. This is another problem sessions video. And in this particular problem, I'm covering a thermochemistry calculation. And we're calculating the heat of a reaction from calorimetry data. Now, these problems always are difficult for chemistry students because there's different types of calorimetry problems. So I want to review that because in some cases, you're actually solving for the energy, the change in energy of a reaction, and sometimes you're solving for the enthalpy of a reaction. And you'll see both of these types of problems in the homework, and you'll also see the enthalpy of reaction problem from calorimetry data next week on experiment 10, enthalpy of formation using Hess's law. So this is a bomb calorimeter. So I discussed bomb calorimetry in section 7.5, calculating using temperature changes in a bomb calorimeter. If you haven't watched that video, go back to week 9's outline, goals and objectives, and watch temperature changes in bomb calorimetry. In that video, we review that the energy of a system is equal to the heat of the system and the work it does. We also discussed in earlier videos that work is the negative value of external pressure times the change in volume. Now, why is this so important? In a bomb calorimeter, there is a constant volume. So there are no volume changes. So what does that mean? Well, if there is no delta V, then delta V is 0. And then the pressure volume work product would equal 0. So if work equals 0, it cancels out. And now the energy of the system, or the change in the energy of the reaction, is just the heat at constant volume. So in your problems, you'll see you have calorimetry problems. Sometimes they'll be asking for the change in energy of the reaction. That's if it's in a bomb calorimeter and it's constant volume, okay? Now, if they give you a non-constant volume, okay, then you're solving for something different. That's typically in what's referred to as coffee cup calorimetry. So coffee cup calorimetry was discussed in section 7.6, enthalpy, which is heat evolved in chemical reactions at constant pressure. So typically in a lab, we're working under constant pressure, okay? Now, if you don't remember these topics, again, go back to week 9, outline goals and objective, and review this concept. But with coffee cup calorimetry, right, constant pressure, so if there's changes in volume, they're typically going to be small. So we're really measuring, we're still measuring temperature changes of the surroundings, but now we're setting it equal to the enthalpy of the reaction at constant pressure. So the difference is I'm solving for, enthalpy is referred to heat of a reaction, and this is basically Q at constant pressure, and we use your Q equals MCAT, or if we're looking at the calorimeter, it could be Q equals CAT. And then if it's at constant volume, like in a bomb calorimeter, then I'd be solving instead of for the heat of the reaction, the energy of a reaction. So let's apply this. Those two videos that we've already discussed, let's apply it to a problem. Now, I'm being nice. This is telling you, determine the enthalpy of reaction from calorimetric data. They might not always tell you this, okay? The first thing is we see that there is a balanced chemical reaction. And now we're starting to see that some of the coefficients are not integers, but rather fractions. So you have to get comfortable with those types of problems. Now, when you read the problem, it says you place a 1.724 gram sample of nitromethane. So the formula, you're not expected to know that, although methane, we do know that there's one carbon, but nitromethane, we put it in a calorimeter and we burn it. And it's in a coffee cup calorimeter. That's why we're doing the enthalpy of reaction. With oxygen, temperature of the calorimeter rises. We see that there's temperature 22.23 degrees Celsius to a temperature of 28.81. So that is a temperature change. The heat capacity of the calorimeter and its contents is 3.044 kilojoules per degree Celsius. Determine the enthalpy of reaction in kilojoules per mole. So this is a big problem. There's a lot going on. So the first thing is you gotta take all this information, figure out what you want. So the good news is they tell you it's coffee cup calorimetry. They don't have to, okay? They do not have to tell you it's coffee cup calorimetry. However, they want you to determine the enthalpy of reaction. So we know right off the bat that the enthalpy of reaction is equal to the heat of the reaction at constant pressure. There is no discussion of a change in pressure, so we can assume it's constant pressure. The enthalpy of reaction at constant pressure is just the heat of the reaction. So what do we need to do? Well, really the reaction is the system. And the heat of the reaction, we can't really measure the heat changes in the bonds when the reaction takes place. We are measuring not the system, but the surroundings. That's typically how we measure these heats of reactions. We're measuring the surroundings, and the surroundings being the calorimeter. So what can we do? Well, we know that the heat that the system releases, and how do I know that it's negative and releases? Combustion is an exothermic reaction, so the Q is negative. So whatever heat the combustion reaction releases, the surrounding calorimeter will absorb that heat. So it's equal in magnitude, but opposite in direction. So we just need to realize the signs are opposite. So the exothermic reaction, the heat released is equal in magnitude, but opposite in direction to the heat of the calorimeter, the surroundings. So what do I need to do? Well, I know that they give me the heat capacity of the calorimeter, and we see that the heat capacity is in units of kilojoules per degree Celsius. Nowhere does it say kilojoules per grams degrees Celsius. This is not specific heat. It doesn't matter mass. It's looking at the entire calorimeter and its contents. So we are not using Q equals MCAT for the calorimeter. We are using Q equals CAT, the heat capacity times delta T. So how do I get delta T? Well, that's why they give me these temperature changes. I have an initial temperature and a final temperature. So now I can plug those in. I plug in my heat capacity, which was given in kilojoules per degree Celsius. I plug in my change in temperature, T final minus T initial. I get the change in temperature, and I'm using my rules for sig figs, so I should only have 3 sig figs as my final answer. So the heat of my calorimeter is 20.0 kilojoules. So it seems like we'd be done, but we're actually not done. Why? Well, they want the heat of reaction not just in kilojoules, but kilojoules per mole. Per mole of what? Well, again, what are we burning? They tell you right off the bat, you are burning 1.724 grams of nitromethane. So I'm given grams of nitromethane. I can convert the amount of kilojoules released by this 1.724 grams of nitromethane into the heat in kilojoules per mole of nitromethane. Now, how would I do that? Well, I plug in the heat of the reaction divided by the grams. I have the grams right here, and I just convert grams to moles. And how would I do that? Molar mass. We've been doing this all along. Now, why do they want the heat of reaction in kilojoules per mole? Well, so that later on we can do stoichiometry. Here's a balanced equation. Here's 1 mole of nitromethane. I want to know the amount of heat, right? I want to know the heat of reaction for this reaction? Well, this reaction has 1 mole. So the heat of reaction is per mole. Now it's going to be in kilojoules. Now, where do I get the heat of reaction? Remember, it's equal in magnitude and opposite of direction to the calorimeter. So now I plug everything in. So the calorimeter was 20 kilojoules. So the heat of reaction, because it's exothermic, in the 1.724 grams that burned was negative 20 kilojoules. And then I see that I convert the grams into moles using the molar mass of nitromethane. The units of gram canceled. I'll be left with moles of nitromethane and kilojoules, so that my final answer for heat of reaction is kilojoules per mole of nitromethane. So this is a classic thermochemistry problem. It's involving reactions, molar mass calculations, Q equals cat, taking in consideration the system and the surroundings, and doing conversion factors. Why do I go over this? Again, you will see these problems on your homework, and we'll be applying this concept for our next experiment 10, enthalpy of formations, because enthalpies, and we'll apply enthalpy of reactions for Hess's law to find the enthalpy of formation. I hope you enjoyed the video. I hope it helps, and thanks for tuning in. This was another session of problem solving.